Assalamualaikum warahmatullahi wabarakatuh. My name is Sheraz Masood and I am currently teaching in Soophia College of Arts and Science 2 first year classes. In the previous lecture, we will discuss about the origin of word physics, introduction to physics, what is physics, and the paper pattern for first year according to the Punjab board. Introduction to physics is topic number 1.1 according to the Punjab textbook board, Lahore. Today we will discuss about topic number 1.2, that is physical quantities and units. Topic number 1.3, that is international system of units, SI units, in which we will discuss about the types of SI units. Scientific notation is also included, and the convention for indicating unit. How can we write SI units? What are the rules for writing the SI units? Topic number 1.4 is error analysis and uncertainty. Okay, now after listening this lecture, the students are able to understand the topic physical quantities, types of physical quantities, the standard units, SI units, rules for writing SI units, system international units or international system of units, base and drive quantities, scientific notation, error analysis and uncertainty. Now we can start about physical quantities. In the previous classes you have already been discussed the physical quantities. What are physical quantities? All those quantities which can be measured or which can be observed, they are said to be physical quantities. They consist of magnitude as well as unit. For example, 4.5 meter. This is the quantity height or simply the length. 4.5 is the magnitude and meter is the unit. It is a physical quantity, numerical value along with unit. This is a physical quantity. Next example is 70 kilometer per hour, as kilometer per hour is the speed. The quantity is speed, magnitude is 70 and the unit is kilometer per hour. Similarly, 33.0 degrees Celsius, quantity, physical quantity is temperature, magnitude is 33.0 or simply the 33, and degree Celsius is the unit. These are the few examples of physical quantities. And how can we measure these physical quantities? For example, temperature is measured by thermometer, mass is measured by beam balance, volume is measured by measuring jug or measuring cylinder, length is measured by inchi tape, by meter rule or half meter rule. And similarly, more examples are time, pressure, energy, weight and volume. There are so many more examples of physical quantities. Before moving towards the type of physical quantities, we can discuss about the system international units. The General Conference on Weight and Measures is responsible for defining the SI units. Their first meeting is held in 1883, while in 11th meeting in 1960. They generalize the certain set of units which are worldwide used. The 26th meeting is held in 2018. Types of basic units, types of SI units or quantities. Basic units comes from the basic quantities. Drive units comes from the drive quantities. Supplementary units by supplementary quantities. Okay, now the basic quantities are the basic building blocks, or simply we can say that the basic quantities are those that are not defined in terms of other physical quantities, whereas the derived quantities are those that can be described on the basis of basic quantities. The unit used by the basic quantities are basic units, and the unit used by derived quantities are called derived units, and the unit used by supplementary quantities are supplementary units. The supplementary units are those, or simply the supplementary quantities are those that are not still decided whether they are basic quantities or they are derived quantities. Here are some examples of basic SI quantities. There are only 7 basic quantities as you discussed in the previous classes: length, mass, time, current, temperature, luminous light intensity, and the amount of substance. Length is a base quantity or basic quantity having unit meter, symbol is m. Mass is a basic quantity, unit is kilogram, kg. Time, unit is second, represented by s. You can remember that second, the symbol for second is not SEC, it is simply S. Electric current, ampere, capital A. Temperature, Kelvin, capital K. Luminous intensity, unit is candela, CD. And the amount of substance is, unit is mole. Now the example of derived quantities. There are many more derived quantities. You can also say that other than these 7 basic quantities, all the quantities are said to be derived quantities. Speed, meter per second, ms minus 1. Force is a derived quantity, unit is Newton, capital N. Acceleration, meter per second, ms minus 2. Area, square meter. Pressure, Pascal. Volume in cubic meter. How can we derive these units? According to the equation, area is length into width. Unit of length is meter, unit of width is also meter. Meter multiplied by meter gets meter square. This is the unit, derived unit of area. Volume, length into width into height. Meter multiplied by meter multiplied by meter. It becomes meter cube. So the unit of volume is meter cube. Density is mass divided by volume. Unit of mass is kilogram and the volume is meter cube. So it becomes kilogram per meter cube, or simply kgm minus 3. Supplementary quantities and supplementary units. There are 2 supplementary quantities which are not yet decided that either they are basic quantity or they are the derived quantity. Pole angle, unit is radian, symbol is RAD. Spherical angle, which is also the solid angle, unit is steradian, STR. Now we can discuss about the radian and the steradian. Radian, it is the angle subtended by an arc. The angle subtended by an arc, this is the arc of length. This arc has a length equal to the radius of a circle at the center of a circle. So the angle is over here at the center. If this angle is said to be 1 radian, if the arc length is said to be 1 radius of a circle. What is meant by steradian? It is a basically 3D angle. It is a solid angle subtended at the center of a sphere. This is a sphere This is the center point. This is the midpoint of that sphere. By an area of a sphere. On the surface of a sphere, each side of a sphere is of length equal to the radius of a sphere. If we consider this surface area over the sphere, each side has a length equal to the radius, then this surface area makes an angle, 3D angle, from the center of a circle is said to be steradian. In general, this is the example. Another example of a diagram, this is a diagram to better understanding of radian and steradian. In 2 dimension, we have this triangle. This angle is in degree, and always remember that 360 degrees is equal to 2 pi radian. If we can rotate this in a circular way, so it becomes a cone, then this angle is said to be steradian. Rules for scientific notation. Rules for scientific notation or simply the standard form. To be in a proper scientific notation or a standard form, the number must be written with a number between 1 and 10, first point, and second is multiplied by a power of 10. Is this a proper scientific notation? No, that is not. What is wrong with that scientific notation? According to the first point, we said that this number must be between 1 and 10, and this number is larger than 1 and 10. So this is not a proper standard form. If we can place a dot over there, then its power increases and it becomes a standard form. We can further consider few examples. This is an ordinary notation. If we convert it into a standard form or simply a scientific notation, we can just write it in this way, as we learned here: a number between 1 and 10 and the multiple multiplied by a power of 10. If the decimal point comes over here, how many digits that point can move? 1, 2, 3, 4, 5, 6, 7 and 8. 8 decimal places that digit can move, that decimal can move, so the power becomes 8. So it becomes 1.37 into 10 to the power 8. Similarly, if the decimal point move towards right, then how many digits it can move? 1, 2, 3, 4. So we have this number between 1 and 10. It moves 4 decimal places, so the power is minus 4 as it moves towards right. Minus 4. 1.37 into 10 to the power minus 4. Next, why does a negative exponent give a small number? Consider this pattern. 10,000 means 10 multiplied by 10 multiplied by 10 multiplied by 10. 10 to the power 4. 4 times the 10. 1,000. 3 times the 10. 100. 2 times the 10. 10. 1 times the 10. And 1. 0 times the 10. It means 1. Anything raised to the power 0 is 1. So 1 over 10 is 10 to the power minus 1. 1 over 100, 10 to the power minus 2. 1 over 1000, 10 to the power minus 3. 1 over 10,000, 10 to the power minus 4. Now, certain rules or conventions for writing SI units. Number 1 point. How can you write The units. The unit named after the scientists are not written with a capital initial letter. For example, Newton, Henry. When you write the full spelling, you can always write the first digit smaller in unit. The symbol of a unit named after a scientist should be written as a capital letter. When you cannot write the full spelling, you can simply write the first letter. Then it is capital. For example, N for Newton, H for Henry, W for Watt. Small letters are used as symbols for unit, not derived from a proper name. If there is not a proper name of a scientist, then first digit must be small. Small m for meter, small kg for kilogram. No full stop or other punctuations marks should be used within or at the end of a symbol. For example, 50 meter, not 50 m dot. This dot is not written over there. That is a standards. Number 5 point. And the symbol of a unit do not take plural form. For example, 10 kilogram. It is not written as 10 kgs. That is not a proper format. When temperature is expressed in Kelvin, the degree sign is omitted. Kelvin is the name of a scientist. So K, capital K, 273 K, this is the temperature. We cannot write it as 273 degree Kelvin. In general, Celsius, degree sign must be there. Degree Celsius, not written as 100 C. C is not a unit. Degree Celsius is a unit, or degree Fahrenheit is a unit. And when you can write in Kelvin, no degree sign is written. So this is not correct. This is the correct way. Number 7 point. Use of solids is recommended only for indicating a division of one letter unit symbol by another unit symbol. Not more than one solidus is used. For example, ms-1 or m/s, j/k mole or j per k per mole, but not as j per k per mole. This is not correct. Only one solidus is used. Here two soliduses are used, which is improper, not correct. We can write j per k mole, j per k per mole, not written as j per k per mole. Number 8. Some space is always be left between the number and the symbol of a unit, and also between the symbols for compound units such as force, momentum. For example, it is not correct to write 2.3 m. Here 3 and m, there is no space. That is not correct. The correct representation is 2.3 space m, or simply kilogram meter per second square, and not in kgm m-2. This is not correct. Space must be written after each letter. Only accepted symbols should be used. For example, ampere, capital A, not as AMP or AM. Capital A is the correct symbol. Second, small s, not as SEC. That is wrong. Only small s is written. Numerical value of any physical quantity should be expressed in scientific notation. If your answer is not written in scientific notation, it is not correct. You can lose marks. For example, 13600 kilogram meter per second per cube. This is not correct answer unless you can write it in a standard form. So this is the correct way to represent the answer. Now, error and uncertainty. This is uncertainty, that you are uncertain which way you can go. What is meant by uncertainties? Every measurement has uncertainty, and also there are three possible ways to write an error. The error may occur due to the following points. When the person is inexperienced, then the error is obtained. If there is a faulty measuring device, also an error is obtained. There is poor experimental technique, also the error is obtained. And the nature of measurement itself, for example, if you can weight the grain of a sand, that is approximately impossible, and error is obtained. There are two types of error, random error and systematic error. What is random error? The random errors are due to the imprecise. The random errors are due to the imprecision of measurements and can lead to the reading above or below the true value. For example, poor technique, different reaction times. And how can we reduce this error? This error can be reduced by using more precise measuring equipment and repeat the measurements. Systematic error. At the end, we can compare the systematic error and the random error so you can better understand. What is systematic error? Systematic error arises from a problem in the experimental setup that results in the measured value always deviated from the true value in the same direction, always higher or lower. These errors are caused by miscalibration or the poor insulation. It can be reduced by comparing the instrument with another more accurate. In random error, there is poor precision as the answers are not close together, but on taking their average, the answer is approximately accurate. Non-specific cause. Cause is not known. The values are too much difference between them. Not reproducible. And the systematic error, poor accuracy, but they are precise. Although they are not accurate, but they are precise. When these three arrows are over there, then it is accurate. So they are precise as they are close to each other. It has a definite cause, that is the malfunctioning of instrument maybe, and it is reproducible. Jazakallah and thank you.